Vanakkam. Welcome to this course on biomedical instrumentation. In the previous video, we started looking at EMG and EMG block diagram. In this video, we will look at EMG circuit diagram, an example of an EMG circuit, and discuss the details of this. Here is the typical two-stage instrumentation amplifier design for an EMG. These are typical preamps. These preamps that are used for EMG are generally of differential type that have good bandwidth. Remember, unlike ECG and EEG, EMG signals are from 10 to 1000 hertz. So, you need to have a large bandwidth. Okay. You can do some computation. Assume that the electrode contact is about 50 kilo ohms, right. If your electrode contact impedance is about 50 kilo ohms and to maintain signal accuracy and amplification, you will need input impedance above 100 mega ohms. Okay. You can compute this. There is math behind this. I am leaving this as an exercise for you, but you can compute this. The input impedance must be above 100 mega ohms. Okay. But present day electronic systems, present day EMG specific amplifier chips easily provide input impedance of the order of 1000 giga ohms, 10 power 12 ohms in parallel with 5 picofarads. So, nowadays this is not such a big deal, 100 mega ohms is not such a big deal. And preferably these preamps must be mounted very close to the participant subject using very small electrodes to avoid any undesirable stray capacitance, the cable related capacitance between the cables and the earth. Preferably they should be on the electrode, also called as the active electrode configuration. This ensures that the signal alone is amplified and anything else that is picked up along the cable, that cable noise is minimal when compared with the signal amplitude. So, these are called as active electrodes. Okay. Here is that typical instrumentation amplifier design. I am giving you an exercise. What would be the gain of this amplifier? How would you compute the gain of this amplifier? Of course, what is the function of this? This is a differential amplifier that essentially detects the amplifies the difference between the two op amps. Look at this, compare this with a highly sophisticated hearing aid. A person is wearing a hearing aid, and let us say he is in a party, a lot of people are speaking and he is only interested in listening to the person opposite to him. Now, all the other persons speaking are picked up by common mode, are picked up by both the ears. The one that he is interested in listening, of course, is picked up by both ears. So, the extra sounds, extra noise that he is hearing from all the other people can be considered to be common mode noise, and that will be rejected, essentially will be subtracted. So, that signal, that component of the signal that is available in both the electrodes will get subtracted, and only the difference between the two will be amplified. That is the fundamental function of a differential amplifier. It is beyond the scope of this course to teach you what a differential amplifier is, how does it work, what is the two-stage instrumentation amplifier, etc. Please do refresh and review these contents for your own knowledge and conviction and understanding. Okay. So, any movement of the cable from the output of the electrode will not generate sufficient noise signal, because and this will then feed into the subsequent amplifier. This is why it is important to place this amplifier very close to the participant or perhaps on the electrode. This preamp essentially provides output with low impedance, and therefore high frequencies will not get attenuated even if relatively long cables are used to connect the preamp and the rest of this. So, very important, because high frequencies should not get attenuated because EMG does have high frequencies. So, the common mode rejection ratio should be at least 90 dB up to 5 kilohertz, right. Usually the commercial models have above 110 dB. One commercial EMG systems have, or at least the spec sheet says that they have 110 dB. One has to measure that and check that. Usually a calibrating square wave signal of 100 millivolt peak to peak at a frequency of 100 hertz is available to check whether this preamp and amp is working properly. The main amplifier has control for gain adjustment from 5 millivolt per division to 10 millivolt per division. So, you can change the gain settings and sensitivity that is most appropriate to the particular muscle that you are recording and the particular situation, whether the patient or the participant, whatever is the condition, based on that you can adjust the sensitivity of the system. With this we end this lecture on EMG, but some points to keep in mind are some of the trade-offs that are there in the design of an EMG system. What are the trade-offs? The general trade-offs that are there. Bandwidth versus noise. How are these two related? How is bandwidth and noise related? Noise power is essentially related to proportional to square root of noise power. Noise power is proportional to square root of bandwidth, something that we know from our basic electrical engineering. Note that CMRR and frequency and bandwidth are also related, is it not? CMRR versus frequency. If you want to maintain high CMRR at high frequencies, then you need exact matching of components, precise component matching. This is critical, and we need this because high frequency are there in EMG, unlike EEG and ECG, high frequencies are there in EMG. So, there is a CMRR versus frequency trade-off, there is a bandwidth versus noise trade-off, then there is the gain and the dynamic range trade-off, common gain versus dynamic range trade-off. We have discussed this previously. Check what this is as an exercise. I am leaving this to you for checking. There is a typical gain and dynamic range trade-off. Then what else? Input impedance versus bias current trade-off. Now, what happens sometimes if you want to have extraordinarily good high input impedance of the order of greater than 10 power 12 ohms, then it may be necessary to use op-amps impedance. It may be necessary to use op-amps that have ultra low input bias currents. Otherwise, you will not be able to achieve this input impedance, because this has to be ultra means what? Extremely low input bias current. So, the regular op-amps will not be able to achieve this input bias current. So, so if you want to achieve high input impedance, a critical criteria is that your op-amp should have extremely low input bias current, something to keep in mind. With this, we come to the end of this video. Thank you very much for your attention.